So welcome back. This is our fifth and last video about graph decomposition. Before we move on to the second strategy for building a joint tree, let's continue with the first one, but let's do a little bit more complicated example to check that our understanding is correct. So we have this Bayesian network here. So usually the first step that we do is to convert it to an undirected graph. So you're going to go from Bayesian network to Markov network by using the technique of modalization. So we see that we have here D have two parents. I need to connect the parents together. H has two parents. We need to connect those parents together. D has two parents too, but they are already connected together, so we don't need to do anything. E has two parents too, A and C, but they are already connected together, nothing to do. So this is our modalized graph or iteration graph, and we're going to work starting with this guy. So we need elimination order, pi, and so we needed to decide how we're going to eliminate the variables here. And what I do is to look at the mean degree. That is easier to understand, and when I choose a mean degree order, I just check if it's not generating filling edges. If it is generating filling edges, I may look at other nodes that have the same degree to see if we can choose another one. So in this graph here, G and H are the nodes that have the lowest degree. So, and if we start with G, for instance, it will not create any filling edges because the nodes connected to G are already connected to each other, so nothing to change here. So we can eliminate G in our elimination order. The next one, we could try H for the same reason. The parents are already connected here, so it will not generate any filling edges. So F, H. And we need to move on. So the next one could be B or C because they also have degree 2. And if we eliminated B, we will need to connect together A and D, the neighbors, but they're already connected together, so nothing to do here, no filling edges, so we can include B. We could go to C now, eliminate C again. The neighbors are already connected together, so C could be a good choice. And now we have a graph that is, so it's a little bit like a mess here, but basically what we have is A, and A will be connected to D, and D will be connected to F. We have not eliminated F yet. A will be connected to E as well, and E connected to F. And also we have this connection here going from A to F. So A and F have a degree 3, D and E have degree 2. So I'm going to select D or E here. Let's use D first, E. So we eliminated this guy here. We can eliminate this E here. So we now have A and F. We can eliminate in any order. Let's say F and A. So this is one elimination order. We hope that is good. We use the mean degree, but we know also that this elimination order is perfect because we did not introduce any filling edges, so it should be very good. So when we do this, we need to generate the clusters, right? So let's think, what are the clusters that are generated by this elimination order? So when we eliminated G, we have to just erase it here, so otherwise it's going to be too messy. So when we eliminate G, so we're eliminating G here in this process. So the cluster will mention D, F, and G. So I'm going to put here D, F, and G. And yeah, because D and F are the neighbors of G, and we eliminate G. All right, so we go to H now, and H has E, F, and H. E, F, and H should be our second cluster. The third cluster will be, we're going to eliminate the B. So we eliminate the B here. We need to connect A and D together are the neighbors, so ABD is our next cluster. Yeah, that's not good the way that I'm writing. Sorry about this, but it's better not to use commas here because there are too many commas. So DFG, EFH, ABD, ABD. Next one going to be C in our elimination order, ACE, ACE. The next one in our elimination order going to be D. So when I remove D here, I will connect to ADF. ADF. And the next one is going to be E, AEF. AEF. And the next one is going to be F, right? So going to be just FA. And the last one will be A. So this is our sequence, the cluster sequence. Now we're going to remove the non-maximal one. So all of those have 3 variables, so do not expect it from these guys here to have a subset. Otherwise we need to have equal clusters. That is not going to happen because we are eliminating variables. But this guy here is a subset of this. It's also a subset of this guy. It's going to be easier if we consider this AEF as the maximal cluster for FA, because we don't need to change anything, the order of the clusters. It's going to be easier. And we can consider that A is a subset of this guy, but it's also a subset of this, and also a subset of this, and also a subset of this, and these two. Again, if we decide to remove to remove A, the cluster A, because of this cluster here, we're going to move this cluster to the end of the sequence. It's easier to consider that A is also a subsequence of AEF, and we don't need it to change anything. So it's going to be like this. So the order is going to be the same: ABD, ACE, ADF, AEF. So this is our maximal cluster sequence. And now we need to connect this thing together. And all right, so let's think about this. So our first node is going to be AEF. So it's going to be the first node of our sequence. And let me just write this a little bit here to give space, expecting to generate the same join tree that we had in the example. So AEF. AEF is our first one. We look at ADF now. So ADF was the elimination of D, and in this case, A and F will happen in this cluster here. So ADF is going to be connected to AEF. Just put here ADF connected to AEF. The next one, ACE. So ACE was the elimination of C. A and E should appear in some other cluster, and it's happening here. So AEF, ACE connected here. We can actually write the separators, right? So because it's actually this intersection results in the separator. So we have just come back here when we look at ADF. It was elimination of D, so AF were happening here. So what's coming here is AF. And again, when we were working with this guy here, we were eliminating variable C. So we have A and E happening here. So A and E is a separator here. The next one is ABD. All right, ABD is it was the elimination of B. So A and D should happen somewhere, and it is happening here. So I'm going to connect ABD to ADF, and the separator here are going to be A and D. The next one, EF age, it was the elimination of age, so EF must appear somewhere, and it's happening here, E and F in the last one. So we're going to connect EF age to AEF. In this case, E and F are the separators. And the last one is DFG, and DFG was the elimination of G, right? And so DF must appear somewhere, and DF is showing up here. So it's going to be DFG connected to ADF, and the DF should be the separator. All right, so this is a little bit more complicated example, but I guess that is enough to understand the technique. Now, we use the algorithm, but we didn't have like the sequence of nodes. We have this more structure that reminds a tree a little bit more. So let's move on and take a look into another technique to generate the structure to assemble the joint tree in the next slide. So the second technique for assembling a joint tree is quite different from the first one, and it uses the maximum spanning tree algorithm in order to achieve that. So the steps are the following. So we start with a maximum cluster sequence, and we generate a cluster graph for this sequence. And this cluster graph is basically a complete weighted and undirected graph. And the weight comes from the size of the separators. So we look here, one example, we have these three clusters, and we generate a cluster graph by connecting every pair of clusters, and we compute the separator and the size of the separator. So the separator here is BC, and the size is 2. Again, here the separator is going to be C with size 1, and here C with the size 1. And interesting to note that the maximum standing tree will generate a tree. That's important because the joint tree is a tree as well. But it's interesting to note that it makes sense to connect the nodes that have the largest separators, because we have this run intersection property between the nodes, and we want to connect the nodes that share a large number of variables. Basically, they mean that we eliminated one variable in that step. So if you look at these two nodes here, if we eliminate A, we have this separator over B and C, and we need to connect it to this guy here. Or if we look at the other direction, we may think that we eliminated D, have a separator of BC, and the BC is happening here. So it makes a lot more sense to connect together the clusters that have large separators than the ones that have small separators, like a separator like 0. They have no variables in common. Why you would connect these two nodes together? And in the case of a maximum spanning tree, we can have ties like we can generate these three here, we can generate these three here as well. And these are both valid joint trees. So in this case here, we can think that, okay, we eliminate A, have this separator over BC. Now we're going to eliminate the two variables in a single step, like B and D, and have a separator over C that connects to the other cluster. So probably here we had an intermediate node here, probably over C and D, and it was considered a subset of this node here. So we compacted, and we are eliminating two variables in a single step. Here is the same thing, like elimination of D. We went to this cluster here, and now we need to eliminate the two variables. That's going to be A and B, and we have a separator over C connecting to this node over C. Probably here we had also an intermediate node here that was over probably A and C, but it was considered a subset of this guy here, so it was eliminated in the process. So we are eliminating two variables together and connecting to C. So even though this algorithm here is a lot more popular than the first one, it is less efficient than the first one. Because we have to create this cluster graph, and this cluster graph is a complete graph. So we need to compute the separators between all possible nodes. Some of these separators will be empty separates because the nodes do not share any variable. So we will not connect this thing anyway. But we need to consider all of them. So that's going to be an n² step. It will be a little bit expensive. And the other step there is computing the maximum spanning tree. It's going to be n log n. That is the complexity of the pring and Kruskal algorithms. So at the end, we have this complexity of n square plus n log n. And if you look at the algorithm that we saw before, it is this is for time, and it's going to be n square because we need to store this cluster graph. So it's going to be n square for space. And the previous algorithm that we discussed is a little bit more efficient. First, because it runs in n square time, so it's going to be O n square time, and it will be only O of n space. It will be linear in space and quadratic in time. So it's actually more efficient both in terms of time and space compared with this second algorithm here. It is interesting to think about a joint tree as a probabilistic graphical model, but a slightly different one. So we have until now graphical models like the Bayesian networks or the Markov networks that were very good to model problems. So very easy to understand them and understand why, what are the independence assumptions they are making, and generating a factorized probability distribution that respects the independence assumptions that we have in those models. But the joint tree is also a probabilistic graphical model, a different one because we usually do not use the joint trees to model a problem. We use the joint trees to answer queries. So, but at the same time, we can understand that the joint tree as a way to specify a set of independence assumptions and also a factorized way to express a joint distribution. And when we talk about the joint trees, they are specifying a set of independence assumptions. So when we have two clusters like Ci and Cj, and there will be a connection between them. This connection is specified by a set of variables that is the separator Cij. And it's important to note here that is the only connection between these two nodes, because we can have a series of nodes in one side here and more nodes on the other side here and so on. But those nodes are not connected to the other side because I cannot have a link that goes from here to here, because if I have it, it's going to be a graph and not a tree, and the joint tree is guaranteed to be a tree. So this will be the only connection. The separator here is the only connection between the nodes, the variables that are occurring in one side, that we call the Ci side of the tree, and the nodes that are occurring in the other side of the tree, that are the Cj side of the tree. So if we observe the variables in the separator, what is going to happen is that we're going to make one side independent of the other side. And that is, remember that what we are doing here is a separation test, because the joint tree is an undirected graph. So it's going to be simpler to understand the independency if we observe the variables that are connecting the two sides of the tree. We are automatically making one side independent of the other, because there will be no influence flowing from one side to the other. So we can make a series of independence assumptions of this form here. Basically, it's a little bit a complicated notation, but these are the variables happening in one side, like the Ci side, and these are the variables occurring in the Cj side. And this is the separator between Ci and Cj. Remember that these are variables only happening in the Ci, because the variables in separator will also happen in both sides, right? They're going to happen in the Ci side and in the Ca side. So, but these are the variables only occurring in the Ci side, and these are the variables only happening in the Cj side. And the separator will make these two sets of variables independent of each other. So just to show you one example here, we have this a little bit more complicated Bayesian network, and we have the joint tree on the other side. If we, for instance, observe A and F, we're going to make this side independent of this side here. Right? And when we look here, A is here, F is here. If you observe these two variables, we're going to disconnect this side from this side. It's actually happening to the other separators too, right? So if you look, for instance, here, it's AD. If we observe AD, let me just erase this. If we observe A and D, if we observe A and D, we're going to be separating B from the remaining of the graph, right? Because B was the variable that was eliminated in this step. If you look here, and if you observe D and F, you're going to observe D and observe F. You're going to separate G, that was a variable that was eliminated in node 1, from the remaining of the graph, and so on. Right? So we can understand this as a set of independence assumptions. They are being stated by the joint tree. And because the joint tree is specifying a set of independent assumptions, we can use these independent assumptions in order to factorize the joint distribution into a factorized form. And for the joint trees, this factorized form has this equation here. So it's going to be this product of the probabilities that were specified by the clusters divided by this product here for all the probabilities specified by the separators. So look at one example here that is slightly simple. So we have this poly tree that have a very simple joint tree for that. So very simple to find the joint tree. So this is the joint tree for this poly tree here. And we can use this factorization to express the joint distribution for this joint tree. So it's going to be the multiplication for the probabilities that I find in the cluster. So we have P of A expressed here, P of C that's expressed here, P of B and A, so we have this cluster here, B and A, the probability of D, B and C, so we have it here, D, B and C, the probability of E and D here, and F and D here, right? It's going to be divided by the probability of the separator. So we have probability of A, probability of B, probability of C, probability of D, and probability of D again, occurring 2 times because we have these 2 separators. And we can try to work a little bit with this factorized form here and see if it is the same as the factorization that was expressed by the Bayesian network. So let's take a look if we can convert one thing into another. So we have here, going to be difficult to write it here, the probability of A, the probability of C, the probability of B, but B and A, but now I need to convert these into the probability of B given A. So we need to multiply by the probability of A. We have the probability of D given B and C, because we have this structure here. So B and C are the parents, so times B and C. And we have the probability of E given its parent times the probability of D times the probability of F given its parent times the probability of the parent. All right, it is going to be divided by everything that we have in the separators, P of A, P of B, P of C, P of D, and P of D again. And we have 2 times P of D because we have these 2 separates, one here and one here. And we can cancel like PA here. We have PD and PD here. So we have these 2 things, and so we can look at and say that we have P of A, that we needed that, expressed here is the unconditional probability distribution. So it's going to be a prior for A, a prior for C. We also need this, that is this guy here. And we have P of B given A, that is this family here. And we have P of D given B and C. And we have this probability of B and C that looks like a problem. We shouldn't have this. And we have the probability of E given D and the probability of F given D. And that is all divided by the probability of B times the probability of C. So what's going on here is that, well, we didn't get exactly what we were expecting. This, basically looking here, let me just erase it, that is becoming a little messy here. So what we have here, we have P of A, so this check, P of C, this check, P of B given A, so this check, P of D given B and C, this check, P of D given D, this check, this P of F given D, this check. But what it didn't check was this guy here and this guy here. And what is going on is the fact that we need to remember that the joint tree is an undirected graph. So it doesn't know anything about this kind of independence that we have here. That's B is independent of C, right? We cannot express this in an undirected graph. But if we know that is true, right, in this case it is true for the Bayesian network, we can say that this guy here actually factorizes. It factorizes into the probability of B times the probability of C. In this case, we can cancel this. So with this extra independence assumption, we can get exactly what we wanted. That is the factorization given by the chain rule of the Bayesian network. Okay, so we got to the end of this lecture. In this lecture, we formalized a series of concepts that we haven't seen before, but we needed to formalize them. And we could show that there is a very strong relationship between variable elimination and factor elimination. We saw that we can convert elimination orders into joint trees and joint trees into elimination orders and preserve the width. So we can use those algorithms in practice because usually it's easier and you have more tools to generate elimination orders than joint trees, so we can convert elimination order into a joint tree and use the joint tree that's guaranteed to have the same quality as the elimination order, but will answer multiple queries over the clusters. We also discussed a series of algorithms to generate optimal prefixes that are going to help to build good quality elimination orders. Okay, if you want to know more about graph decomposition, you can read chapter 9 of the textbook. And in the next video, we're going to change subject and I'm going to start talking about map and MPE queries. So see you soon in the next lecture.